So this video is a pretty important one. It's an important topic in calculus. Continuity. So we'll see that the definition of mathematical continuity is pretty similar to what you think of when you think continuous means just in everyday language. So we saw that a limit is when you're approaching some value on either side. And if the function takes on that value at some x value a, then we're going to end up calling this continuous. So basically these are ones where we could do direct substitution. So a continuous process is one that takes place gradually without interruption or abrupt change. And here's our definition of continuous. Okay, this is going to be a very important definition, one that you are going to want to have memorized. So a function f is continuous at a number, we'll say a, if the limit as x approaches a is the same as the y value when you plug in a. So in other words, your limit is the same as when you plug it in. So what that kind of breaks down into is you have to check three things to make sure it's continuous. And these are the three things you'll always want to check for continuity. First, is the function defined at that x value? If it's not defined at that x value, then it can't possibly be continuous at x value if there's a hole or an asymptote. Next, can you find the limit as x approaches that value a? Third, if both those first things are true, is the value of f of a, so in other words, the y value of the function, is it equal to our limit value? If that's the case, then we are dealing with a continuous function at that value a. Now, when we're talking continuous, and you don't need to write this, just you can kind of look at the picture and listen. These changes as we're getting really close to a for our x values, so in other words, as our x's are getting really close to a, our y's are not really changing by that much. Okay, they should be pretty similar too. So that's kind of what we were talking about no abrupt changes for our continuity. Now in this picture, we want to see where it's discontinuous and why. Well, the first place we're discontinuous is at x equals 1. And the reason we would say why is we have a hole there. A hole can be picked out from an equation when you have parts that cancel out. So if there's a factor in the numerator that cancels with a factor in the denominator, that's what creates a hole in your graph. The next time we have a discontinuity is at x equals 3 in this picture. This would be because of a jump. And then our last point of discontinuity would be x equals 5 in this case. Even though we're defined at at x equals 5, our value of f of 5 is not equal to our limit at that value. Therefore, it's not continuous. So this would be another hole. Essentially, the first one, x equals 1, breaks our first rule. It's not defined at x equals 1. At 3, we break the second rule. The limit as x approaches 3 does not exist. And the third one, x equals 5, breaks our third rule. The limit is not equal to our y value at 5. So now we'll look at some of the equations. And we want to see where is it discontinuous. Well, when you have a rational function, the places it would be discontinuous are what makes the denominator 0. So we know x equals 2 is going to be a discontinuity. We've got to figure out what type. If x minus 2 is a factor that will cancel out, we will get a hole. If it does not cancel out, then we'll get an asymptote. So we'll want to factor the numerator, which factors into x minus 2 and x plus 1, all over x minus 2. The x minus 2's cancel out, So therefore, x equals 2 will be discontinuous, and we'll have a hole there. At b, the graph of 1 over x squared looks something like this. And then we're saying at 0, our y value is 1. Well, our limit as x approaches 0 of this function would be infinity, because we're going up forever on each, and our y value at 0 is 1. So the limit does not equal your y value, therefore it is discontinuous at x equals 0. Okay, so we have an asymptote there. The third one here, if we take our limit as x approaches 2, this is what we worked with in letter A. We saw that would eventually cancel out into x plus 1. So now with direct substitution, this limit is equal to 3. Well, our limit of 3 is not equal to our y value at 2. So therefore, our third part of our definition of continuity fails. So at x equals 2, we will be discontinuous because the limit as x approaches 2 does not equal f of 2. Okay, what we would have there, we would have a hole. So that would be the situation that has a hole, and then you've got a point somewhere else. Now our last one, this is the greatest integer function that we saw earlier this year. Our y values took on the integer that was less than or equal to the x value you were working with. So for example, like 1.1 would take on a 1. 1.4 would take on a 1, and so forth. When it then gets to 2, it'll jump up to 2. So we have jumps at every single integer. So this is discontinuous at all integer values. And our reason, because we have the jump, is continuity. Okay, and here's some different pictures of our discontinuities we could have. The first one, we have an open circle here at 2. So therefore, that's a hole. The second one, that's what we just saw. And again, these are the 4 that we just looked at a second ago. We've got our asymptote there. The third one, we've got a hole, and then it's defined somewhere else, so your limit does not equal to the y value. And then the fourth one, we've got our jumps. So again, these are the 4 graphs that match the 4 situations that we just did. Now, just like we can have limits from the right and left, we can look at continuity from the right and the left. A limit is said to be continuous from the right, or a function is said to be continuous from the right, if the limit from the right is equal to your y value. So it's usually easiest to see with a little visual. This function here at 2 would be considered continuous from the right, because the hole is with the left-hand part, the solid circle is with the right-hand part. So what this is saying is, coming from the right, it ends up taking on the value that you're approaching. The second part there, continuous from the left, is when your left-hand limit is equal to the y value. So we could do this same picture, but just make the solid circle with the left-hand part. And now this is something that would be considered continuous from the left. So basically, if the solid circle is with the left-hand part, we could say it's continuous from the left. If the solid circle is with the right-hand part, we could say it's continuous from the right. So our jump discontinuities, we can look at and see, are we continuous from the left, are we continuous from the right? In this case, these jump discontinuities, they are all continuous from the right. Because if we're approaching from the right, our function ends up taking on that value. From the left, we end up having a hole. Okay, and we've seen a couple examples of jump discontinuities now. We've got the step function here, and we had the one in the example where it jumped up as well. Now we can also say that a function is continuous just on a given interval. So maybe we want to limit it to just a certain set of x values and see if it's continuous just on that section. So we say a function is continuous on an interval if it's continuous at every number in that interval. If a function is perhaps only continuous up to one of the endpoints, then we understand that it's continuous at that endpoint. So an example of that would maybe be like a square root function, for example. Square root of x looks something like that. It's not defined to the left of it. We can say it's continuous at its endpoint there, meaning that it's continuous from the right. Now, usually the interval examples we'll look at will be closed intervals. So, for example, like from 2 to 5 or from 1 to 3. And we'll see, okay, from 2 to 5, is the function continuous just on that interval? If, for example, beyond 5 was not continuous, if it's not defined there, we could say that at 5 we are continuous from the left. Because as we come from the left, it does take on that value. In the second one, on 1 to 3, say maybe 1 was not defined. We could say from the right it is continuous. Now, some theorems about functions that are continuous. Say you have two separate functions, f and g, that are continuous. If you add those functions together, they will still be continuous at your value a. Same thing if you subtract them, if you multiply by a constant. If you multiply the functions together, it'll still be continuous at a. And same thing with division, provided that when you plug in a into g's function, it's not 0 because that would make it undefined. A couple common functions we'll see, polynomial functions and rational functions. A polynomial function is continuous everywhere. So a polynomial would be something that kind of looks like this. Maybe as an equation, you may have like x to the 5th plus 3x squared plus 7x plus 1. Okay, that's a polynomial. Got many terms raised to different powers. Okay, those will always be continuous. So you could either say on all real numbers, or you could say from negative infinity to positive infinity. A rational function is continuous everywhere in its domain. So for example, if we had y equals 2x plus 3 over x minus 1, the one x value that's not in the domain is positive 1 because it would make the function undefined. So that means by our theorem here, y equals 2x plus 3 over x minus 1 is continuous everywhere except for at 1. So if it's in its domain for a rational function, then it is continuous at that point. So we're going to show that this function here, 1 minus square root of 1 minus x squared, is continuous on the interval negative 1 to 1. Well, think of this as a y. If we subtracted the 1 over, we would have y minus 1 equal to minus the square root of 1 minus x squared. Now, if we work to get everything over to one side, we would have a negative y plus 1 equals the square root of 1 minus x squared. Square both sides, you've got negative y plus 1 squared equals 1 minus x squared. And if you added the x squared over, we now have x squared plus negative y plus 1 squared equals 1. What this is this is a circle whose center is 0, 1 and has a radius of 1. Now, because we were dealing with the negative square root back here, it's just the bottom half of that circle. Sometimes it's tricky to see that here. It might be easier to think of it back in the original. The square root of 1 minus x squared, that being negative, is the bottom half of the circle. And then the 1 shifts everything up 1. So our picture kind of looks like this here. It's the bottom half of basically a unit circle shifted up 1. So first off, our function is defined from negative 1 to 1, because that's what we wanted to show. We wanted to show it's continuous from negative 1 to 1. The limit also exists at every point. So it's defined at every point. Our limit exists at every point. And since everywhere from negative 1 to 1, we can do direct substitution, that means f of a will equal the limit of a. Therefore, this will be continuous. So it's continuous since the limit as x approaches a of f of x is equal to f of a for all a that are in between negative 1 and 1. Now remember, at the endpoints, we think of it as continuous from the left for the right-hand endpoint and continuous from the right for the left-hand endpoint, because it's not defined beyond those values. That's all for today's video. We'll see you next class period.